Welcome to BKW Physics. I'm Mr. McConley, and today we're going to broach the idea of work. Now, here in New York State, we're coming up on Christmas break, and it still has not really snowed here. But normally at this time of year, it snows. And when it snows, a lot of people end up doing a lot of physical work. You got to shovel the driveways, you got to shovel the walkways, you got to plow out, you got to do a lot of work. Now, other people say, yeah, that's work. I can see how shoveling snow is hard work. But I do a lot of homework every night, and that's work. I do a lot of paperwork. I like English. I do a lot of writing. That's a lot of work to get a paper done. It is a lot of work. But in physics terms, you didn't do any work. So what we have to define in physics terms is how do physicists define work? And it all starts with James Prescott Joule. James Prescott Joule was an English physicist, 19th century, and he defined work as we use it today. The way he defined it is it's the force exerted on an object times the distance that the object moves. So simply put, I'm not going to write it out in words, I'm just going to write it this way. This is the way you see it in your reference table. Work is equal to the force times the distance. So, if you are applying a force to anything, okay, like a marker here on the shelf, I apply a force, it moves a distance, I'm doing work. But what about the example where I push on this wall? I'm applying a force. Distance moved, 0, work, 0. And that's where people get fooled all the time in physics problems, is they'll give you an example like, Ivan the great weightlifter is lifting weights at the Olympics, okay? And Ivan the great weightlifter picks the weight up and then holds it over his head for 10 seconds. How much work is he doing when he holds it over his head for 10 seconds? And the answer is, he's not doing any work. Now that seems so ridiculous, because if you've ever held something heavy over your head, you know how hard you're working to hold it up there. But since he's not moving at a distance, according to the definition, he's not doing any work. So back to James Prescott Joule. He defines this. Distance is in meters, force is in newtons. So work is in newtons times meters, right? Okay. But he wanted his own name on it, so he used J, joules. So the units for work are joules. Now, if any of you have paid an electric bill, do they do it in joules? Mm-hmm. Do they do light bulbs in joules? What do you see joules on? Heat. Okay. So back in chemistry, you did like Q equals MC delta T, right? Or Q equals MHF, one of those. And when you got the answer, there was a certain amount of heat. The heat is in joules. Well, what you're going to find is that this work here to be equivalent to heat. So if you move something a distance with a force, you can say this is an equivalent amount of heat, energy, and we'll get into that later. I'll explain that more. The other thing you got to realize is, I always like to relate it to a graph. If you have a force and distance graph, or force and distance graph goes like that, or whatever. So you apply a force, moving distance, whatever. What is this going to be right here? This area? Well, if you think about it, if you're doing the area, and you're doing this times this, you're doing force times distance, aren't you? So the area of a force-distance graph is work. So sometimes you'll see scenarios where force times distance is work. Let me just grab a bowling ball here quick from the side, because I want to relate a few things. And goes back to the concept where if I grab a bowling ball, a 16-pound bowling ball, pretty heavy, and if I pick this bowling ball up, I'm picking it up, I'm applying force, I'm moving a distance, I'm doing work. Now when I eventually get it up to here, because I'm getting ready to, bowl, when I'm holding it right here, am I doing any work? No. Does this ball contain energy though? Oh yeah. Because if I drop it, okay, I just touched it to the ground. If I drop it, that thing make a noise. Bowling balls are pretty heavy, they're going to hit the ground pretty hard. This definitely has energy, but you wouldn't know it because I'm just holding it there. That's potential energy. When I drop it, it starts to fall. What type of energy? Kinetic energy. So, work, say I did 20 joules of work to lift it up. How much potential? 20. How much kinetic right before it hits the ground again? 20. So what you're going to notice is that work, kinetic, potential energy, all can start being equivalent to one another. I'll come back to that idea also later, because we got to go into it in a little bit more detail. The next thing is, a lot of times when you're doing work on something, it's not such a straightforward relationship. Like, say, you're mowing the lawn. We've already done a problem like this previously in an earlier chapter. You're pushing a push mower, right? Here's the handle of the push mower, and I don't know that lawnmower well, something like this. Okay, there's the mower. Grass along the side. Okay, there, you're mowing the lawn. And you're pushing along like that. Now, you're pushing with a force, and I'll draw that in red. The force is this way, isn't it? Is that 100% of that force, is that moving you forward? No, when you think about it, the force is this way and the distance is this way. And we already learned a bunch of times this year that when force and distance don't match direction, you can't just use them together. If this is 20 and this is 10, you can't just multiply them because they're not in the same direction. So where are you going to have to go with this? You're going to have to do components. Good call. And so if I focus in just on the force here, and I make a little triangle of it, like we've learned to do, which part of this is going to be the matching part to the D? The stuff on the bottom, which I'll call it horizontal force, FH, because it seems like it's horizontal to me. And all I would need to know is the angle. So if that's 30 degrees or whatever, and I could do a little sine, or actually I would do cosine. I would do cosine is adjacent over hypotenuse, and I can figure out what this was. And then, in this case, the work would be the horizontal force times the distance. So what I'm pointing out, I'm not giving you real specifics, I kind of did it generally. What I'm pointing out is you got to match your force and your direction have to be the same way. Like, if you pick up that bowling ball again, and pick up the bowling ball and you walk sideways with it. Now, am I moving the distance? Am I applying a force to move? Do the two match? Well, no, they don't really match because I'm like pulling upward on it, but I'm moving sideways with it. See how the two aren't really matching? So when you do these problems, you got to get the force and the distance to go the same way, and once you got that, you just multiply them together and you're done. Easy. But sometimes the trick is in getting them the same direction. Let's do one example and then I'll cut this video off. Some real numbers here. Say you got a ramp. And there's some 30 Newton mass. Weight. It's Newton, it's really weight. Some 30 Newton weight sitting on the ramp. And you are applying 40 Newtons. And that allows you to just push it up the hill, up the ramp. The ramp is 13 meters long. The ramp is 5 meters high. And I want to know how much work is done against gravity. Work against gravity. How do I do that? Well, work is force times distance. Okay, that's always easy to pull out. But which direction is the force? Which direction is the distance have to be? And the answer is, if you're talking about gravity, they both have to be vertical. So I'm definitely dealing with this vertical distance. It's going to be the 5. The 13 is really not going to make a difference in this case. And which force am I dealing with? Is it the 40? Is it the 30? if this thing weighs 30, which way is the weight pointing? It is the 30. The 30 is the one that's pointing the same direction as gravity points, because the 30 is the weight. So really all I'm going to do is do 30 newtons times 5 meters. And when I multiply those together, I can get now, I could ask it differently though. And remember, Newton meters is joules. Okay? I could ask it differently though, and I could say, how much work did it require to push the weight up the ramp? See, that's a different question. Because if I'm saying how much work did it take to push it up the ramp, then I'm going to use how far I'm pushing up the ramp, and I'm going to use not 30, but how hard I'm pushing it to make that happen. So I would use these two multiplied together if they're asking me how much work did it take to push up the ramp. It's the way the question's asked, and that's the key of what I have to say for today's lesson. So